All right. So today, 29. Hyebin will lead us on section 2.2, or continuous discussion and lecture. And then myself, and then Tahir, right? And this is on Wednesday, right? So we're gonna have class on Thursday. Oh, no. Wednesday is Thursday. I'll be in Japan then. Okay, right. And then I will have a long business trip, but only one online. It will be my 2 a.m. in Chicago. We'll try, right? So myself and Tahir and chapter 7. Homework will, I already prepared for this week. When is the homework due?
Next Monday.
Huh?
Next Monday.
Next Monday. Then next Wednesday, so same day. Right. I will provide. And presentation when I return back. Alright. So we will start the second round of your lecture and discussions from today. Second round. Any question on schedule? No? Then David. Yes.
Hi everyone, my name is Hyebin Kim. I speak here the lecture about feature in manufacturing. So I start the lecture. I refer to the textbook, and chapter 6 is feature in manufacturing. So I will cover from 6.2 to 6.4. There are several issues about the definition of manufacturing features. First one and second one was introduced by Professor in previous lecture. So I will introduce the ones that follow. Third issue is dimensionality. The dimensionality of manufacturing feature is related to the relationship between features and process models. Most manufacturing process is related to volumetric manufacturing features. For example, drilling process is related to the hole, which is volumetric features. And also there are many lower dimensional features like surface, edges, and so. For example, the face milling is related to the surface. So which is the two-dimensional feature. And edge, for example, the welding process is related to the edge, which is one-dimensional. This is the part of ball bearing. So there are some features about ball and bearing surface. So you can see the volume and surface manufacturing features. And fourth one is completeness of feature model. When all the geometry of a part belongs to a feature, we can say that it has completeness of feature model. For example, this part has many geometry, but only holes and surface is used to define the manufacturing features. So we can think that it doesn't have completeness of feature model. So it is another issue. And this one is feature relationship. This is the geometric relationship between the features about dimensioning and hollow lensing. So it is to perform geometric reasoning. For example, the question like what is the direction of machining? So there are two parts. So they have structural primitives. So we can know that the top face of left part is related to the top face of second part, right part, and also we can know that looking at the slot of left part, we can know that the direction of machining is from the one end to the other end. And this is the intermediate geometry. So we can know the geometric relationship between features. For example, cylindrical disc and through one. So we can know the feature axis of cylindrical disc is collinear with the feature axis of one. So we can know the relationship of features. And sixth one is temporal ordering. So manufacturing needs temporal ordering before manufacturing. There are two types of precedence relationship. One is end-start relation, and the other is start-start relation. About end-start relation, for example, there are two processes, A process and B process. A to B means that A process must be executed before B process. And about start-to-start relation, two processes must start simultaneously. So there are some examples of first the left one. There is a picture of a contents alcohol. There are three processes, so it must be executed. They must be executed in this order. And we can know the temporal. We can make the temporal ordering using data structure. So we can know that the pattern must executed after the feature is made. And second one is product family. Product family is a collection of parts similar enough to each other to have similar manufacturing requirements. So for example, there are generic parts and variant parts. First level is about a general concept of a part. So we can know that the part needs testing and features to machine. And And the second level is about variant part. So you can know the specification of part. Actually, this shows the specification of product family. So in this product family, there are casting and features about 4 cap. And third one is about variant part instance. In this, it includes the actual part which are satisfy the specification of product family. So it includes the actual part instance. Any question? And next chapter is about generation of manufacturing features. So there are some methods to create manufacturing feature. I will introduce them. First method is interactive feature identification. This is simply picking method. So the designer pick geometric elements of a geometric model is placed on the computer, and then manufacturing features are identified. Many people say that this method is relatively immature than the ones that follow. And second method is design by manufacturing features. This method is to design using manufacturing features. So, in first class system developed by Cutkosky, it used design the method of this method, but there are some problem by assuming that the designer creates the part model directly in terms of its manufacturing features. There is no conversion or extraction of manufacturing features. So the designer is forced to design in terms of manufacturing. So there is less freedom to design. In cap system developed by Mantira, it provides some solution. So in this system, it can change the specification of feature, but it cannot judge whether the feature is changeable. This system is described in detail in chapter 11. And also this method, in this method, only negative features are available. So it is called destructive solid geometry. So sometimes it can be represented, the features can be represented using subtraction operator in CSD3. So there is some problem. And third method is design to manufacturing feature mapping. It is to get manufacturing features directly from design features. So designer has more freedom to design than previous method. So the mapping method is described in detail in chapter 7, but most people prefer the next method, which is manufacturing feature recognition. there are advantages like complete separation of concern between design and manufacturing. So the designer have more freedom to design, and the design recognizer can create several alternative models of the part. So it gives the planner freedom of choosing the best plan. For example, this is a simple staircase part model, which has two interpretations in terms of manufacturing. First one is this, the other is this. So the recognizer can create two choices of manufacturing. So the planner can choose the one according to cost or the other point. So it helps the planner choose the best plan. And chapter 6.4 is group technology coding. Group technology is called GT, exploits similarity among parts to classify parts into part family. So GT code is a kind of abstraction of part specification. So they use GT code to represent part data. So, for example, of GT code, this is the table of GT code about this model. So, first digit is shows general shape of this part. So we can know that this part is rotational part. And the following digit shows the specification and specific information. And we can represent this part using GT code 11106. In Hyde research, this paper says that GT can effect considerable cost saving by eliminating design and process plan duplication, automatic part data retrieval, and reducing the number of changeover in tuning and fixture by scheduling similar parts together. Also, GT schemes are usually partly or fully hierarchical. So it is like decision tree. One of the GT schemes, the class developed by Alan, but there are some problems. The process is not automatic, so it includes human intervention. So parts can be classified differently by different people because of the way the person responds to a question. This is the problem. So solving the problem, many people have developed the code by Hyde, Henderson, and so on. Because the GT code is useful for design and manufacturing. This is my lecture. And then question.
How similar do the parts have to be classified together as a family?
GT code?
Yeah.
How similarity?
How similar do they have to be?
So, assuming two parts of rotational parts which are rotational, so they have same code one. So you can know that this they are in the same class, and then they also are judged at this stage. So we judge whether they are similar and provide a code to them. So they can be classified using the similarities. This is your question.
What's the question again?
Like how similar do the parts have to be, or in other words, maybe if there's any differences, how much difference can you tolerate?
That's true.
I think it will be based on generic shapes.
Shapes. Like she said, on the codes, because we are talking with respect to the GT scheme. So it depends on the code that the scheme generates.
You have a Lego box, hundreds of pieces, and spread out on the table, and then start to grouping. Right? How to do that? Depending on your choice. Also, maybe if you talk about Google image search, how do they rate similar images? Depending on color or depending on shape or feature? The feature is important concept there. Or fingerprint. Fingerprint. How do you find out the real match? So all the similarities check. There are many. It's still complicated.
Okay.
Right. Okay. Right. I have four observations from Hyebin's presentation. Page 5, volumetric manufacturing. In reality, everything is 3D. There is no 2D in real world. Point is an idealization. There is no point. Surface, there is no real surface. In mathematics, we are using idealization. How much the volume of point? There is no volume of point. What is the sequence of plane? There is no sequence. So it is not real world. It is an ideal world, idealized world. So what can be the surface in 3D? Okay, 3D. This looks like a 2D surface. Okay, 2D surface. It's moving. Okay? Moving. Surface. This is surface. Curved surface. It is a surface in 3D. 2D in 3D world. We call this a three-dimensional plane. Three-dimensional plane. Do you understand what I mean? There's no real 2D in the world, in reality. Everything is 3D. Okay? So manufacturing is talking about 3D. Designers can use idealized word, right? But in manufacturing, everything is 3D. So 3D curve also, right? There's no line, right? This is not 1D. It's 3D. 3D curve in the space. And you need to have a thickness and diameter to realize that line in real world. Right, this is a mathematical idealization. This is one thing I want to share. The other one is this one. The uniqueness of manufacturing. Unique in manufacturing, temporal ordering. Time in the real world is linear, and you cannot change the order. No, it's one way in real world. But we are talking about reordering or process. There is only idealization. Before manufacturing, we can change orders to optimize the design. But in real world, there is no such way. Right? I want to change my age. So I want to be young. 10 years reordering, right? It's not possible. Right? Real time is real world, one-way sequence. No reordering. So there is manufacturing. Manufacturing is fully linear timing and no reordering. But this is only for pre-planning stage. Pre-manufacturing. Before the real manufacturing. So I cannot be younger, right? And then 16. Right, 16. She says about destructive solid geometry. We learned about constructive solid geometry. CSG. The other one, yeah? DSG. DSG is destructive. Not popular name. You can think about this. Only negative. And 18. Freedom of designers. You can think of fashion designers. They are thinking of very fancy fantasy words, right? So you can think about chocolate house. Any can be. You can imagine any fantasy, but how can you manufacture them? That's tough problem. So I found this picture on the Google Image. Many films about chocolate words. Chocolate war? I don't know what this is. The Charlie chocolate pattern is famous. Right? That is my end of document. And then moving on to my part 5 and 6.
그런데 이한라 씨가 지금 보고 있는데 소리가 잘 들린다고 하고 있거든요.
불이 꺼져도 소리는 계속 전화.
소리는 어차피 얘로 녹음을 하는데 이제 소리 지금 확인하고 있는데 다 잘 들리더라고요.
이제 불이 켜 있을 때하고 꺼졌을 때하고 차이점이 있냐고 나오고 싶은 거죠.
그거는 그냥 전기가 꺼진 거고요. 2차로 추가로 이제 소리를 녹음하기 위해서 사용하는 건데
1차로 이걸 하려니까 1차로.
근데 이제 지금 이걸로 해도 잘 들리는데.
아니 나는 1차로 이걸 해달라니까 왜 그걸 안 해주냐고.
네, 알겠습니다.
처음부터 내가 하기 시작할 때부터 요청했는데.
충전하도록 하겠습니다. 충전이 지금 안 돼요. 네.
그러면 차이가 나는 거지. 불이 켰을 때하고 꺼졌을 때.
그거 꺼진 거죠 지금은.
꺼졌죠.
네. 네, 지금은 이제 꺼져 있는데.
그래서 그 차이 나는 걸 나는 알고 싶어. 여기서 녹음된 소리하고 저기서 녹음된 소리의 차이점 듣고 싶은데.
그럼 녹음을 다 한 다음에 체크해야 될 것 같아요.
아까 켜 있었잖아요.
네, 이제
그때는 이 소리를 됐었냐고 녹음을.
아니요, 그때도 아닙니다.
그럼 뭐를 켜고 이걸 달고 있어 내가.
교수님께서 그거를 요청하셔가지고.
아, 이거를 녹음해달라고 요청을 한 거죠. 학기 초부터 내가 이걸로 녹음해달라고 요청한 거잖아.
그게 그 전 학생이 이제 그걸로 했었지 않습니까?
네.
근데 그 방식대로 하니까 녹음 그 장비가 좀 고장났는지 잘 안 되더라고요.
그럼 새로 사라고 있잖아, 내가 그래서 그러면.
네, 알겠습니다. 수입 거 새로 구매하라고 하겠습니다. 그리고 네, 근데 그 어플 그 예전에는 그 제일 처음에 썼던 게 권순조 박사님이 썼지 않습니까? 그때는 동영상 그냥 녹화만 하고 이제 후처리를 이제 자기네 그 권순조 박사 컴퓨터에서 작업해서 그냥 올리는 용도였으면 괜찮은데 지금 실시간 스트리밍을 하지 않습니까? 그럼 이제 그거는 녹음기입니다. 녹음기.
이게 왜 녹음기야?
그게 녹음기입니다. 그게 소리를 받아서 저장하는 용도고요.
이게 불로 가는 게 아니라고?
네.
컴퓨터로 가는 게
네,
아니라고?
소리는 지금 예로 받아서 이 프로그램이
아니, 이거 무선인데?
네, 녹음기입니다. 이제 무선 녹음기고요. 그게 레코드입니다. 그냥.
그럼 이 안에 메모리가 있다고요?
아니요, 이제 그게 컴퓨터랑 이 선을 연결하면 그 소리를 받아서 이제.
그러면 컴퓨터로 가는데 왜 그 상시에 같이 녹음하면 되지? 무슨 소리야?
이제 그 스위브 프로그램 이제 어플을 저도 써봤는데, 김인규 씨가 저번 시간에 썼지 않습니까? 저번 시간에 그걸로 쓰고 스위브 어플리케이션을 써서 영상을 촬영했는데, 스트리밍을 하려면 결국은 다시 이 OBS 프로그램에 넣어서 이제 송출을 해야 되는 거고요. 그 사이에 뭔가 소프트웨어적인 문제가 좀 있습니다. 요즘.
다음에 나중에 봅시다. 그럼 이건 여기 갖다 놓고 하는 거야. 난 이거는 당연히 녹음되는 줄 알고 멀리 빼라고 했던 거지.
그래서 저번에 네, 교수님 됐습니다.
그러면은 이거는 우리 원격 텔레컨퍼런스 할 때 쓰는 그 독일 덴마크 제 그 스피커가 아니냐?
로지텍 겁니다.
또 다른 거야 그러면?
제일 처음에는 이걸로 썼던 걸로 알고 있고요. 요즘은 다른 장비 혹시 쓰시나요?
덴마크에서 사온 무슨 이렇게 생긴 걸 쓰고 있었는데 텔레컨퍼런스 할 때는
그건 제가 아직 못 봐가지고 이건 스텝 센터 쪽에 한번 물어보도록 하겠습니다.
이거 오잖아.
그거는 예전에 저희가 화상회의 할 때 스텝 센터에서 이걸 사서 사용을 했었거든요.
스텝 센터에서 빌려온 거예요?
네.
로지텍이었나?
네, 일단 제가 아는 장비는 로지텍이었습니다.
하여튼 로지텍이면
네.
이거는 저 카메라 저 무빙하는 글럼하고 따져온 거죠?
네, 맞습니다.
근데 이게 안 된다는 거잖아, 믹싱이.
네.
그러면 로지텍에서 제공하는 이놈이랑 호환되는 무선 마이크가 있을 거야. 이놈이랑 연대.
마이크요?
그래. 그 이놈이랑, 이놈 어차피 마이크잖아요.
네,
스피커도 되지만 마이크 기능을
네.
지금 우리가 쓰는 거잖아.
네.
그럼 이놈이랑 연동되는 마이크가 무선 마이크가 있을 거라고.
마이크는 어차피 그 무선 마이크 아무거나 써도 상관없어요.
하여튼 믹싱이 안 된, 이걸 왜 안 되냐고. 지금 안 된다니까 그러지. 예? 아무거나
네.
쓰면 안 되는 일이니까.
네.
이거랑 호환이 되는 무선 마이크 하나 사서 하면 돼. 그럼 이게 같이 믹싱이 돼서 들어갈 거 아니에요. 이게 들어가면 같이 들어갈 거.
네, 알아보겠습니다. 찾아보도록 하겠습니다.
원래 이런 회의할 때 여기다가 여러 개 연결해서 큰 회의하면은
네,
여러 개 연결해서 쓰거든요.
네, 맞습니다.
똑같은 원리죠. 무선으로 하나는 무선으로 연결하는 거. 유선으로 여러 개 하나 연결하듯이.
네, 찾아보겠습니다.
Alright, 6.5. So we are finishing up chapter 6 today about manufacturing. And then next week, on Wednesday, we will see the data exchange between the feature data exchange between CAD and CAM or other. Right? I'm trying to talk about process planning and assembly planning. We already see many different classes about process planning, CPP, and also assembly, so it can be easier. So, process plan should be done before real manufacturing. So, design product can be manufactured. So between design and manufacturing, we need to have a process plan. I talked to you this one many times. Right? So here is the process planning here. And design. And then what else? And machining. So real machining is here. Right? Real machining. So you can say these are steps of process planning. But the main part can be adaptive process planning. So anyway, between manufacturing and design, you need to have a process plan. Key stages, selection of manufacturing technology. You want to say for the assembly, you may use welding, or you may use a bolt and nut, or clipping attach, or other ways. Right? So you need to select technology how to manufacture, or milling, or drilling, or welding, and then the sequence of the technology. What can be done with it? So, in real world, as I said, time is linear and no reordering. Only planning stage you can do. So, you need to have a clear sequence. And actual processes. These processes are a little bit smaller part of activities. So sequence of technology is bundling, grouped blocks, and then inside the block you need to have a more fine process. And then sequence of processes, right? Sequence of technology, sequence of processes. And then resources, what kind of machine, who is doing, and where, the space, location. As I told you before that, same Volkswagen Golf car can be manufactured in 30 different factories around the world. Same Golf car. In different space, different people, different machine. Right? So, but the same product. So you need to find out what kind of resources you are using for manufacturing. When and where. And then parameters. Speed, diameter, or else there are many. Temperature, humidity, right? Light, and detailed test plan of the process. When I visited Germany 2 years ago, they showed us special work cell. Very simple, one single work cell. But the difference is because it is adaptable to human worker. Say I'm old, right? So that my eye is not so good comparing to yours. I cannot read small characters, and it is better when the light is brighter. But comparing to young guys, my eye is a little older, right? So when the new work, the same stage, same work cell, the people are changing because of the work shift or other reason, right? Then the work cell recognize who am I by using ID or scanning or I don't know, somehow, right? Then adjust according to my body condition, lightness, height of chair or something like that. Adaptable work cell for the optimal operation. It is very similar to a car seat configuration. That the good, nice, expensive car, then you can memorize the configuration of seat. Say my wife and myself, we are driving together same car, right? When my wife is riding, she needs to change seat and angles and distance. But one button, then they can change. Near future they may recognize myself and my wife and then adjust automatically. Right? That kind of thing is parameter settings. Process planning, same. So design and machining, in between we have a process planning. There is scheduling and control. Right? Scheduling means a time sequence. You cannot change in the real world, right? Sequence is schedule. Timing, linear time steps. Types of process plans. There is a variant process planning and generative process planning. Variant is starting from old plan. It's same as designing, right? You can have a variant designing, variational design. You start from old design that is very similar and modify something and then produce. That is a variational designing, variational process planning. Use a group technology coding scheme to map a proposed new design into a code of existing plan. So you start from existing plan and modify according to, you should identify each part by using something like a coding or some variational parametric. Generative design is very new one. You don't have any previous one. So you maybe solve the all the system of equations in one step, or you may learn optimization software code algorithm to arrive at your own new design, new process plan. Another feature of process planning, so input is design package, output is a machining operation plan, same. Process plan is in the middle, but there can be more constraint, mechanism, facility layout, knowledge, industrial engineers, tool gauge, and also input. This is input, right? Intelligence, time, part programming, process planners, and then output is machine code, machining code. 6.6, assembly plan. Also, I told you many times, assembly planning stage. Assembly method is a bonding, welding, or bolting, clipping, and sequence planning, time step, and then operations planning is access direction, the details, parameter settings, fasteners. So conceptual design stage, and then process plan. You need one of the process plan is assembly process. If you are not good, then you arrive at quality problem, efficiency problem, cost problem. I told you many times, CQT is the most important part of any manufacturing or design. CQT, cost, quality, and time. Time. This is most important three parts of all the machining or manufacturing or industry. So you arrive at quality problem, cost problem, and performance problems. And there is a wording called design for assembly. See, design for assembly. Objective is reduce the number of parts in a machine. So you are a designer. How to make it more good for manufacturing. Okay? I want to design, but designers also in the one part is want to be a freedom, right? Fantasy, new idea. Chocolate house, or fantastic car, right? But in another part, you need to consider about the manufacturing. How can you make chocolate house? Right? How can you maintain the chocolate house? Okay. So this is all about for manufacturing, design for manufacturing. So objective, one of the objective can be, so the most important objective can be this one, cost, quality, and time, right? For designers. But one of them, they may have an objective to reduce number of parts. Same performance, same quality, but reduce number of parts, that's better. For manufacturing, for assembly. Right? So 3 conditions to determine a part is in this special. Then you cannot delete this part. This part is must. You cannot delete engine from the car. Right? So indispensable part. What are they? They have 3 conditions. Is it the moving part? Is it a different material, same material, different material? It can be separated, then you can remove sometimes. Right? Or how can you separate? Mechanically separate or chemically separate? So in this way, in this process, for design for assembly, features are used for data retrieval, object reasoning. This is used for good help for design for assembly. So is one of the slides coming from process planning for assembly. Right? Simple. The motor, plunger, bolting, assembly. Exploded view. in key items in design for assembly, we need to, if possible, I want to minimize the number of parts without functional performances degradation. And then sometimes it can be a sub-assembly, or some part or portion of the product can be made as a module. Sub-assembly. So main board can be designed as a separate module. Then you can outsource them. You can order from China and then assemble them here, right? So modular assembly is also an important concept there. Fastening, mechanical fastening, bolting can be replaced by bonding, by chemical bonding or welding. It's simple. Then it can be one part. It can be one part. You don't need to have another process. Introduce guide and taper for ease assembly. Guide. No. Projection holes or slots that will cause some problem with identical part, then can be avoided. Very similar but different. But sometimes for the assembly it can be confusion. So that A must be here, but sometimes B is here because it is very similar. So as a designer, you need to have a separation by using, say, color or other way. So for this, you need to use symmetric. So symmetric means it's same. So it can be interchangeable. So A and B is same. So you need to use anyone. Or it is not available, then you need to exaggerate the differences. This is a trend of car manufacturing. So many cars are using more modules. They are saying modular platform. Modular platform. Platform is something like a underbody. So main functional body, including engine, braking, and fuel, and something like that. Which is sometimes you can say not shown to customers. Usually not shown to customers. Customers are exposed to outside color and body, curved surface, and dashboard, audio system, sunroof, and leather chair, right? Interior is important for them. But engine, brake, fuel, it is not shown. It is important, but usually not shown to him, right? So they choose a car usually by some observable part. They are saying this is body. So you need to have many variational parts on the body part, but the platform part can be same. As far as possible, you make a single. There is the idea between separation between body and platform, and then still we separate our modular architecture. We can make another longer lecture about modular concept if we have time. I put on the schedule. Assembly sequence planning, operation planning is a little bit lower level. Pass planning, sequence, assembly need to have a pass because it is 3-dimensional, right? In this way or in this way. So pass is important. Feature provides solution to issue assembly planning. So feature concept is also important. Rough assembly pass or final assembly for access direction, and then free space for access geometry. This is the shown that the orientation is direction, access direction is most important, right? You cannot do in this way. Only way is you need to in this way, right? And also this part is only in this way or in this way, only two directions. Right? Similar, plugging is only one way, special shape, right? And also this one. You need to to assemble. If you are trying to make this assembly sequence as a automation, automatic assembly by using robot, then you need to have a very good planning before. If your human is doing, let them go, right? But robot is not so good. You need to have a clear planning. Question. Then type.
Hello guys, I am Tahir Abbas Jauhar. I will be leading today's discussion session. So, we have discussed different things up to now, like 2D drawing, 3D CAD files, different types of analysis, generative design, and we have a little bit idea of CNC machinings, and there are different types of CNCs like 1 axis, 3 axis, 5 axis, etc., and 3D printing. So my question is, what could be next?
Mind directly connected with the design. You think and machine starts designing.
Wiring into the brain and then produce.
Actually, the one researcher in MIT, he made this device. He put like on the ear, and it gives it the commands just for other tasks. So I think that technology can be integrated in the future.
IoTs, or my idea is digital twin. So it is like the physical model but a virtual model, and it will have all the data like CAD model, FEA model, and FMEA model, and it will be connected with the physical system. So this is a definition that it is a connection between physical and virtual model, and the connection is establishing real-time data based on sensors. So something like that. Here is another pictorial view. So I will show this. This is just a little. It will show from the concept design to the manufacturing stage. As you can see, this is just a seat design for the car.
Best.
And the next is linked with its FE model. So then it's CFD. And then it's manufacturing. So everything in the virtual environment. Next thing is about manufacturing. So we have seen the model, and this is the virtual twin that is manufacturing the model. Like the manufacturing system, and here comes the actual system that is manufacturing the Soonhung.
Is this in real time?
Yeah, and the whole idea is the real-time connection between virtual system and
Same time. Simulation and versioning.
And the software is NX?
It is Siemens Solutions, not NX. NX CAD-CAM, but they have some other solutions as well. So my question is, what could be the benefits of this technology? It looks very cool, but how will it be beneficial for design and manufacturing?
It's a good type of prototyping. You do not need to make an actual product to test before manufacturing.
But we are working
Simultaneously?
in physical and in virtual.
I have a question.
Yeah.
Did they use the sensor for simulation? Using sensor?
Yeah, right. It's like real system, sensors, which send data to the virtual system.
Maybe for manufacturing more complicated products, you can use this method instead of using some manufacturing recognition method automatically, since maybe for the complicated products using computer might be longer, possibly.
So, how should we select our products for this technology? Like for the cell phones, can we make digital twins?
For smaller parts, for tiny.
There
For
should
the
be a
chips.
criteria, right?
Yeah, size or complexity based
Yeah.
criteria. How micro you want to go.
It is good to change the manufacturing process because it helps we know the correct process. It is helpful to make the decision for the point of change.
So, can you give any examples of the system that would require digital twins?
there can be a lot of systems, I mean, from automobile to aircrafts to ships, even the plants can have.
Right.
I don't know what kind of system uses this, but maybe if the manufacturing requires, for example, a high temperature environment, and you require to curve the mold in that environment.
But it is not limited to manufacturing only. It is for operations and maintenance as well. So I do something. Ways for these not
No sound.
You use laptop sound.
It is not okay.
Oh, it's coming. More louder.
Foundry Bureau. First, a bit of background. This digital twin is virtual. We integrated it in an offshore wind turbine, the Alliad 156 megawatts. GE currently uses just analytics to monitor the turbines. Each alarm must be validated by an operator, and this is difficult and expensive because these turbines are offshore. Our demo focuses on a digital twin of the yaw system. It consists of 7 motors. Each motor operates independently, so we have created 7 twins. We have created 7 virtual temperature sensors, 1 on each motor, in order to collect the temperature data of each individual motor. We started with Maxwell in order to do an analysis of the thermal properties of the motor. The resulting 3D physics simulation was used to detect and compute the maximum temperature on the coils. Next, we used Workbench to create the reduced order model with current as input and torque and maximum temperature as output. Here is the actual 3D simulation of the motor that was created. The ROM of the motor is brought into the system simulation platform ANSYS Twin Builder. You can also see that the input used to create the ROM and the output from the virtual sensor result in the expected lifetime of the motor. Now we are running the actual system simulation in ANSYS Twin Builder. On the left side of the screen, you see the input of the temperature on the coils, and on the right side of the screen, you see the remaining lifetime of the motor being calculated. As the simulation continues to run, you can see the temperature of the coils going up and the remaining lifetime of the motor decreasing. Now that the simulation is complete, we need to generate the digital twin. Here you can see the code that is the digital twin being generated by ANSYS Twin Builder. This code is integrated into GE Predicts for complete predictive analytics. And here are the twins of the motors that comprise the yaw system of the wind turbine. Let's take a look a bit deeper into one of the motors, motor number 1. Here we can see the current, the temperature, and the remaining lifetime of the motor based on the operating conditions of the motor in real time. This is hypothetical. Let's switch to motor number 4. This motor is overheating as indicated by the red area. Here the temperature of the motor is too high, and we can actually take a look at what will happen to the motor if it continues to operate at this high temperature. The remaining lifetime of the motor is going to decrease significantly. Why is this important to know? Without this digital twin, the wind turbine operator has to physically send a technician to inspect the motors. Expensive. The digital twin provides all of this information remotely and in real time. The operator can now plan when to replace the motors. There is no guessing or physical inspections needed any longer. Imagine the savings that the turbine operators will realize by implementing digital twins.
So the key idea is of saving. So the salary of a wind turbine technician is $30,000 to $50,000 per year. But what are the pricing of the solutions? Do you have any idea?
I think no matter how much they cost, over the long run, they will be cheaper than hiring technicians.
Well, you may be right, but alone, if you consider just the software, then it will not solve the problem. You also have to hire someone to work on that software. So, but it is beneficial with respect to life.
I have a question.
Yeah.
Why only the software and digital twin needs some hardware as well? Like sensors and maintaining the system, the data, real-time exchange.
Yeah.
So that also adds.
Yeah. So, anyways, I could not find out the pricings. I searched, but so my next question is relating to job markets. What essential subjects should mechanical engineers study? How this system will affect on the job market?
I think the main area where this can be applied is performance analysis in many sectors, actually, energy or I think for energy sector, like fuel cells or something, you can do simultaneous performance analysis. That is one area where this can be applied. And also for automobiles or planes, ships, transport, basically.
This may lead to the end to this mechanical term, like it may become mechatronics.
Technical aspects.
Yeah. This may lead to the end of human civilization. Well, I think that we should think about these subjects. We should at least learn one of them, because they will be included in the industry environment somehow. Here is how will be the
digitalization is changing everything. Enterprises need to react and become digital enterprises. Siemens offers solutions for the digital enterprise. In this age of disruptive innovation, manufacturers need to drive digitalization from the idea through the factory all the way to the customer. Siemens PLM software can help. Your journey starts with Team Center, a platform that fosters collaboration and accelerates innovation. Team Center helps manage requirements and workflows, work with suppliers, leverage systems-based design, streamline manufacturing, and more. Smart design is essential for today's smart products. Siemens software promotes systems-driven development that integrates mechanical, electrical, software, and electronics design. And breakthroughs like convergent modeling help you create a dynamic digital twin of your product that transforms downstream processes. In engineering, the digital twin helps predict performance with simulations for thermal behavior, airflow, and more, and physical tests for factors like noise and vibration. In manufacturing, product and production digital twins interact to optimize global operations on the fly. You can design new layouts, balance assembly lines, analyze worker safety, and assess robot performance. This ensures that production runs at peak efficiency before it even runs. The benefits of driving a digital enterprise also extend to production. With virtual and real worlds tightly aligned, you can optimize production with MES, prove out automation performance, 3D print real products, and achieve closed-loop manufacturing. The value of PLM doesn't stop with production. Data analytics help you analyze your whole process, including the customer experience, so you can uncover the next idea that can disrupt your industry. This is real digital transformation.
So this is the complete idea. It's
nice videos. Best industry is best. All right, see you on Wednesday.